Hello, Gregory. I'm the tutor for EGME 335, and I figured I'd go through just a quick little example here for you of second order kinematic coefficient stuff. So this first part here is just going to be on the first order part of it, of like figuring out your angular velocities. So this is what I wrote up as an example. Let's see if I can make it a little easier to see here. So in this problem, we've got a fixed base with one link like this, another link like that, and another one pointing down. And link 2 is our input. It's just a pretty simple 4-bar mechanism. So first thing I did was I drew out my free body diagram, just on first instinct. And so what I'm assuming we know in this problem is we know the angular velocity of our input link, and we know the angular acceleration of our input link, which is link 2 in this. And I also assumed that we know all the lengths and angles theta. So that way we just don't have to work through any geometry of figuring this out. So what do we not know? We don't know omega 3, alpha 3, omega 4, or alpha 4. So know nothing about the angular velocity and acceleration. So now I've written up my vector loop equation over here. R1 plus R2 plus R3 plus R4 is equal to 0. And so for R1, it's just a fixed flat link. It's just the ground. So we know the angle of it, which is going to be flat. And we know the length of it because it's not going to change. It's fixed on both ends. R2, that change in angle is our input. And the length will stay the same because it's just a linkage. R3, we don't know the angle, but the length is going to stay the same. And R4, same case. So we don't know the angle, no the length. So next up, I convert that into its respective axes. So in the x direction, in I hat, we have R1 cosine theta 1 plus R2 cosine theta of our input plus R3 cosine theta 3 plus R4 cosine theta 4 is equal to 0. And the j hat direction is the same thing, except instead of working with cosine, we're just working with sine. And so I'm doing this all entirely based off that presumption I usually make that I've mentioned before, that I measure from tail to tip and counterclockwise for my angles. So, you know, let's say I have a link like this. I go like this to the right, and then I measure from the tail counterclockwise towards the tip. And same thing goes for this. By keeping it consistent, I don't have to worry about plus or minus signs. Having an angle like this will naturally give you the plus or the minus for the respective directions of it. So that's how I'm working with this. So yeah, that's why I'm just working with sine and cosine like this. So then I derive with respect to our input angle. Let's see, can you still see it? Yeah, okay. So when we derive with respect to our input angle, we don't need a chain rule or anything because we're working with our input for our derivation. This one right here is a constant, R1, and derivative of a constant is just 0. So that gets canceled out. R3, well, for R3, we're going to do something similar to our input angle, except because we're deriving with respect to something else, we have to chain rule on a theta 3 prime. And it's the same exact case for theta 4. We have to chain rule on a theta 4 because we're taking the derivative of this but we're also right here trying to take the derivative of d theta 3, which we're not directly doing. So we end up having to come up with a way to make this work, and that involves chain rule. So effectively what you end up saying is d theta 3 times d theta input over d theta 3 is just equal to d theta input. That's effectively where this comes from, more or less. You can see that. So after we've derived it that first time, all we need to do is convert it into a Jacobian matrix. So what that's going to involve is we're looking for, what are we looking for in this? We're looking for theta 3 prime and theta 4 prime. So we're going to go ahead and take every coefficient in front of those terms and put it into a matrix. And then anything that doesn't contain that is going to be moved over to the right side. So R3 sine theta 3, negative R4 sine theta 4, and R3 cosine theta 3, and R4 cosine theta 4 all have those terms in front of them. And then this has none of that, so it gets moved over to the right. Now, where does this form come from? I've had one or two students ask me, like, how did I go from this to this? Well, the way that you can sanity check yourself to make sure that you've done this right is this and this multiplied by this, just doing matrix multiplication, should return you to this. So R3 sine theta 3 times theta 3 prime gives you that term right here. R4 sine theta 4 negative multiplied by theta 4 prime will give you this right here. And the same thing goes for if you multiply that by that, and that by that, you'll end up with that. So that's how you can figure out how to get to this form from that form, or how you can double check. Now, like I've said before, and I've shown in previous videos, I'm a big fan of just using your calculator from this step forward, or just using MATLAB. You set this equal to A, this is X, and this is B, and you simply say that X is equal to the inverse of A multiplied by B. But if you want to do it by hand, you could do it by hand. It's not too terrible for a 2x2 matrix. It's still not very good though, honestly. So we've got to multiply 1 over AD minus BC in our matrix. So in our matrix, lowercase a is this is D, this is B, I believe, and this is C. Yes, A, B, C, D. So what we end up doing is A times D, so that upper left term times the bottom right term minus the upper right term times the lower left term. And because there's a negative sign there, that just becomes a positive. And then in here, you have to flip the positions of this. So D goes up here, A goes down here. And then B over here becomes negative B, and C becomes negative C. So you flip these two terms up here, and then you put a -1 in front of these two terms. And then you have to multiply it by that right-hand side from the Jacobian matrix. And when you do that, you will get what theta 3 prime is and theta 4 prime is by hand. Now, I'm not going to carry on with this step because that's just a lot of work, especially in variable form, to do this times this multiplied by this whole thing right here. But what I will show you is just a really quick example matrix multiplication in general. So you do these two right here, these two and these two first. And so 1 times 5 gives you 5. 2 times 6 gives you 12, and you add those together. 3 times 5 gives you 15. 4 times 6 gives you 24. Add those two together. And I'm multiplying by a scalar on the outside here just so that you can see an example of that. And so add those together, and then factor in the scalar. So you just multiply all terms by that 1 over 2. And you get 17 over 2 and 39 over 2 for that example. So that would be how you would go about finding omega 3 prime or theta 3 prime and theta 4 prime. Now from there, all you're going to have to do is say that omega 3 is equal to theta 3 prime multiplied by your input angular velocity, and similarly theta 4 prime and your input angular velocity. So you can figure out what those are. So relatively simple for that step. Next up, I will erase this and we will carry on with this problem. Solving the second order kinematic coefficients, which will be very similar. All right, so second part of this problem. So I derived it a second time here. Now it's important to keep in mind that you need to use the product rule when you derive the second time, because now you're not just deriving sine of theta input or sine of theta 3. Instead, now you're having to take the derivative of sine theta 3 times theta 3 prime. So you need to apply that product rule where you take the derivative of that first thing, multiply it by the normal thing, and then add the normal multiplied by the derivative of the second thing. So for I hat, you're going to end up with negative R2 cosine theta input minus R3 cosine theta 3 multiplied by theta 3 prime squared minus R3 sine theta 3 theta 3 double prime minus R4 cosine theta 4 times theta 4 prime squared, because you basically are getting this again, but then you're multiplying a second theta 3 or theta 4 on, so it becomes squared. And then the other thing is with that product rule, if you're taking the derivative of just that theta 3 prime, you're going to get theta 3 double prime minus R4 sine theta 4 times theta 4 double prime is equal to 0. And you do pretty much the same thing for your J hat, and you get something very similar. And then I moved it out of the standard Jacobian form and put it into the solvable form over here. So theta 3 double prime, theta 4 double prime is going to be equal to the inverse of this matrix, because this is what's contained with that. So you're going to have the inverse of this matrix multiplied by this, which is the orange here represents everything that does not have one of these variables impacting it. So it's just basically the constants. And you're going to be needing to use the primes to figure it out. And then from here, once you solve all this, hopefully not in variable form, but with actual inputs, once you solve all this, your theta 3 double prime and your theta 4 double prime, you can use to figure out what alpha 3 and alpha 4 are. All right, well, I hope this helped, and have a nice day.